going to our second presenter for today, Marjan Temovski. He's a researcher at the ICAR Center in Debrecen, Institute of Nuclear Research. Bogdan, could you unshare your screen? Yes.
Okay. Thank you, Arthur, for inviting me to speak. First, thanks to Bogdan for his nice presentation. I will talk about some of the things he mentioned. So he already explained some of the things, so it will be nice just to continue over that. My presentation is about hypogene karst systems, including stable isotopes and application of stable isotopes to the study of hypogene karst systems. So, although it will be mostly about how do we apply them to the study of hypogene karst system, a brief introduction on or overview on the stable isotopes, and it's actually a continuation to the same thing that Bogdan was talking about. So I suppose all of you are aware up to now about what we are actually talking about, or when we are analyzing or studying the stable isotope composition of certain compounds. We are actually expressing them as a ratio of the heavier, which is a rarer isotope, to the more common one, the lighter isotope. And here are just few of them added, few of the elements and some of the most common isotopic ratios that we are dealing with, and the notation in which it is given, the delta value, which is giving our sample ratio expressed against the already determined standard value. So, for example, here, as Bogdan was also talking about, the oxygen isotope values, for example, the delta O18 value, if it's expressed as a, let's say, 15 per mil VSMO standard, it means that we have that our sample has 15 per mil more oxygen 18, or the heavier isotope, in it compared to the standard. We will actually be talking about all of these isotopes here and some of their application to the study of hypogene karst systems. Few more things. So the main essence behind all of this is that the process of isotope fractionation, where the composition or the abundance of these isotopes will split between two substances or two phases from the same substance. And generally, just to have a general note, the heavier isotope will be more concentrated in the denser phase. This is the characteristic thing. And there are a lot of phenomena which are causing these isotope fractionations between compounds, between substances, or the different phases of the same substance. For example, the isotope exchange reactions, the most common, let's say, the so-called equilibrium isotope fractionation will happen. So it's controlled by the thermodynamics, so it will be controlled by temperature, let's say, or kinetic processes, which mostly are the result of the reaction rates, causing so-called kinetic isotope fractionations. The interesting thing is that because of all of these processes, we will have a situation in the environment, nature, then certain environments will have a characteristic isotopic signatures, and also certain processes will cause characteristic isotopic effects or fractionations. When we combine all of this, we can use the stable isotopes as a tool to identify certain sources, certain processes, and so we can actually study a system based on the composition, on the isotopic composition. Switching towards our main topic, the karst systems. And before going to the hypogene karst, just a brief note on karst. You already had a nice overview from Bogdan on caves and karst, but just a small note. So we have this specific terrain formed in these soluble rocks. Mostly it's limestone or carbonate rocks, but it can also form in other soluble rocks, like let's say evaporates, like gypsum or salt, etc. And what is interesting, we have a specific surface topography which will form, and also extensive subterranean drainage. So the water goes underground and creates all these nice caves, as you can see here, for example, on the picture. And it's specific because it's an evolving system in which the caves are the product of this process, of this dissolution of the rock, but also they are the carrier of this process. So when we talk about evolution of karst, we talk about cave evolution, which we call it the speleogenesis as a term. So all of these are more or less, in essence, the same. And when you talk about the most common caves that you have seen in pictures, or you visited touristically, will be actually what we call epigene karsts, or traditionally the so-called normal karst systems, where we have the drainage, the recharge of the system, the supply of water coming from the surface, and also we have the main source of the capacity of the water to dissolve the rock is coming from the soil, or from the air and the soil, as actually it was nicely illustrated by one cross-section in Bogdan's presentation. And you can find this kind of images characteristic of this epigene karst systems. On the other hand, so again, this upper part, this blue covered part, will actually represent our epigene karst system. On the other hand, there is another type of karst systems which are actually recharged from the bottom, from below the formation, the soluble formation, let's say the limestone is recharged from the bottom. And the source of acidity actually are various gases, which are from origin from depth. And actually the formation of these karst systems or cave systems are much more complicated than the epigenic in terms of processes happening. So there are a variety of geochemical processes and mechanisms under which this operate. So contrary to the epigene karst systems, which we can, even when they're active, we can easily visit many of them and study even underwater caves, etc. In hypogene karst, usually we cannot access them. The active ones are deep below, and we don't have an access to them. So most of the time we are only able to study fossil systems which have been already intercepted by the surface. And the approach to study them is to identify that they have been formed by these hypogene processes is by their specific morphology. There are some characteristic forms, features which identify them, like, I don't know, the cave pattern, or some smaller forms that you can find, like cupolas, or this half-ceiling, half-tube channels on the ceiling or the walls, or feeders, etc. But this can be sometimes ambiguous, because also some epigene processes can create similar features. So it's not proof enough that these caves have formed in this way. More certain ways to study the cave minerals and speleothems found in these cave systems. For example, here on the picture, you can see the bedrock in which this cave was formed, then a layer of calcite coating, and also that was covered by a layer of gypsum, which indicates two phases of cave development. And these are characteristic minerals for this kind of hypogene karst systems, as we will see later. So that's much more certain way of determining whether a certain cave was formed in these hypogene processes. Two most common genetic types of hypogene karst caves or hypogene speleogenetic processes can be found: the so-called hydrothermal carbonic speleogenesis, or hydrothermal carbonic caves, and sulfuric acid caves, or sulfuric acid speleogenesis. The first one is formed by dissolution of carbonic acid, but as I said, not the acid, or the CO2 is not coming from the surface, it's coming from depth. And On the other hand, the sulfuric acid speleogenesis is due to oxidation of hydrogen sulfide, which is also coming from depth, forming sulfuric acid, which dissolves the rock actually. So in this kind of systems, it will be the stable isotope composition of sulfur, carbon, and oxygen. And we can study them in gas, liquid, or solid compounds, although most commonly it will be solid compounds. So cave minerals, that is speleothems. What we can find out from the stable isotope, from their stable isotope composition, we can identify the sources of the gases. We can identify uncover a lot of information about the water rock interactions. We can reconstruct some of the speleogenetic environments. For example, we can reconstruct or calculate the temperature at which they have formed. And also we can gain a lot of information on how these processes operated. Although I said mostly it's based on cave minerals, this application of stable isotopes, if we have an opportunity, if we have an access to a spring discharging such hypogene karst system, or we have an available borehole going deep to that karst system, so we have access to the water of an active hypogene karst system, we can also study the geochemical properties, the stable isotope composition of that water, or certain compounds within that water, some dissolved ions, for example. And here you have it noted in a red color, some of the characteristic positions or aspects of this kind of a karst system to which we can apply stable isotopes to identify certain properties of the karst system. To begin with, the karst functions by water dissolving the rock. Of course, the water has some acidity, so some dissolved acids, but in essence, it's a water going through a fracture and dissolving the rock. So also the properties of the water can tell us something about that system. And the application of stable isotopes in this is pretty much the same as in any kind of groundwater system or other karst groundwater systems. So what we know that almost all of these waters are actually of meteoric origin based on their stable isotope composition. So that is the delta 18O or delta 2H. So the hydrogen stable isotope composition or the oxygen stable isotope composition. Most of these waters will fall on the so-called meteoric waterline, which mostly is the local meteoric waterline, so it's characteristic for the local precipitation where the recharge of those systems happened. But in addition to that, the original composition can be modified, can be kind of altered by certain processes, of which most characteristic in these kind of systems will be the exchange with the bedrock, with the carbonate rock exchange due at high temperature conditions. There will be an oxygen exchange between the carbonate and the water. So the composition of our water in this plot, let's say on oxygen and hydrogen, it will be shifted towards more positive value on the oxygen, but the deuterium will not be changed, or the hydrogen will not be changed, because there is no hydrogen in the carbonate rock. On the other hand, another significant process to modify the composition of the water can be an evaporation. For example, if it's a pool of water at the water table, let's say the discharge part of this hypogene karst system, we can have an evaporation, which our remaining water will be enriched in both oxygen and hydrogen heavy isotopes. Just one note. On the other hand, the information that this composition of the water it gives, it's the recharge conditions or the source for this karst system. So in essence, if it wasn't modified, and if we can determine the age by radiometric, by applying radiometric isotopes, we can also use even these systems for paleoclimate reconstructions. I will talk a bit more in detail about this hydrothermal carbonic speleogenesis, this type of hypogene karst. It's more common of these two main ones which I mentioned already. It forms by dissolution of carbonate rock by rising thermal water, and the process by which the dissolution happens. So the acidity increases by the cooling because of the inverse relationship between calcite solubility and temperature. These systems are generally really rich in CO2, so the concentrations of the partial CO2 pressure is very high. So compared to let's say epigene karst systems where the source is the soil, so it will be lower than the 0.05 atmosphere partial CO2 in this epigene karst system most commonly. And on the other hand, in this kind of system, we have much higher values. I mean, even going up to almost up to 1 atmosphere. So what is interesting about this system is that at depth we have an increase as the water rises. We have due to the cooling, the solubility increases, so we have a formation of passages. But as it goes closer to the surface, due to the lowering of the pressure, we will have CO2 degassing, and the water will be oversaturated, so the calcite will start to precipitate, and we'll have a situation like here in an already formed passage, which is actually a strongly fracture controlled passage of something like 1 meter, let's say, width. We will have deposition of thick calcite coatings as a result of that degassing of CO2. In terms of stable isotopes in this kind of system, what is generally done, it's the study of a stable isotope composition of the carbonate minerals. That's the most commonly applied. Although, as I said, if we have access to the groundwater of this kind of system, we can also study the stable isotope composition of the dissolved inorganic carbon or dissolved organic carbon if there is, or also we can study the stable isotope composition of the free and dissolved gases available in the system, which can give us a lot of information about how this system functions. The main information which we can get, for example, from the carbon stable isotope composition, we can identify the sources of the CO2. We are talking about the deep-seated sources, but what is the actual source, how this CO2 was formed? We can obtain some information on that, but also we can identify certain processes that might have modified this original carbon isotope composition. In essence, whether there was some kind of a kinetic effect or it was only under equilibrium isotopic fractionation. And also from the oxygen isotope composition of the precipitated carbonate minerals, we can gain information about either the water oxygen isotope composition or the temperature from which it formed. One of the other, if we know one, we can also calculate the other one. I'll show you some example later. Here's some small overview of the possible sources of CO2 in this kind of systems. Most commonly, it will be a metamorphic CO2. So CO2 formed by the decarbonation of carbonate rocks at depth at high temperature. And as you can see here on this nice overview graph, you can see the characteristic isotopic composition of some of these sources. For example, the metamorphic CO2 will have generally positive values above 0 per mil. On the other hand, the soil signature, the soil CO2, what also Bogdan was talking about the C3 plant CO2 formed from C3 plants or C4 plants will have much more negative values. So it's easily distinguishable whether it's one on the other, even on the isotopic composition, let alone the concentrations. But we can have also contribution of magmatic CO2. For example, from the mantle, which has a kind of a narrow range between something like -4 to -7, 8 per mil although that overlaps slightly with some other, it can overlap with other sources, or generally due to mixing, if there is also some additional soil contribution, which is possible, as we originally this water is recharging the karst formation from the surface. So in that system, we will have some kind of contribution of the soil CO2. Based on this, we can have different types of minerals with different carbon isotope or oxygen isotope composition based on their temperature formation or based on the source of carbon. For example, you can see here some examples. Let's say if there was a CO2 which formed by oxidation of methane, we could have even more negative values, as you can see also on this graph here. Or as I mentioned before, we can have some positive values if the source is coming from metamorphic signature. On this graph at the top, you can see modeling to obtain the value of the deep-seated CO2, in which we have springs where deep groundwater from hypogene karst system is mixing with the surface water, and we have certain ratios of mixing of up to, let's say in this, we have up to 75% of contribution from this endogenic CO2, for which a value characteristic of metamorphic CO2 was obtained. On the other hand, we can use their isotopic composition to identify water rock interactions. The bedrock in which this cave was formed, due to the interaction between the water can have its isotopic composition altered. For example, you can see this nice profile here where the oxygen composition of the unaltered, here marble bedrock, and then the shift towards much more negative values, which reflect the values of the fluid with which it had interacted. But on the other hand, the subsequently deposited flowstone here is actually much more positive, and this is formed by much younger processes in an epigenic karst environment. So this cave was originally hypogenic, and then it was shifted in much shallower positions, and it was overtaken by the epigene processes or overprinted by epigene processes, and a normal Vadose flowstone was deposited on top of it. We can find many other examples when we have this kind of alteration trends. What is most commonly is the shift of both oxygen and carbon values towards more negative values. This is the most common, which especially for the oxygen, which is reflecting let's say in a higher temperature system, it's reflecting the higher temperature of the water, which will have more negative value. But also we can have a situation in which let's say like this trend seen here, when the oxygen is shifted to more negative, but the carbon is shifted to slightly more positive, which will reflect the interaction with the carbon composition of the fluid was higher. So different source of carbon in these two systems, it can be identified. Furthermore, if we combine the carbon, as I said, if we combine the carbon and isotopic composition of the oxygen, and if we have prior knowledge, let's say, about the water from which precipitated, we can, for example, obtain this by studying fluid inclusions, the water composition, stable isotope composition of fluid inclusions, by applying theoretical or empiric calibration curves. We can calculate the temperature at which this mineral formed. You have I put an example here, for example, a calcite, which has this -15 per mil expressed in PdB scale isotopic composition. And if it precipitated under equilibrium conditions, and the composition of the water was -10, for example, it would have formed at the temperature of around 38-40 degrees Celsius. On the other hand, this sulfuric acid speleogenesis, it's a specific system in which the dissolution of the rock is by sulfuric acid, and the source of this sulfuric acid is this sulfuric acid is formed by oxidation of hydrogen sulfide. I mean, it can form also by oxidation of other sulfides, for example, pyrid. But more extensive cave systems haven't been really found it hasn't been found to be such a potent agent, although it can have a significant impact. But typically in this kind of caves, it will be the oxidation of a hydrogen sulfide gas originating from depth. And this oxidation can happen at the water table, I mean above or below the water table, but most of the cave formation has been found that it happens above the water table, where we have degassing of this H2S and dissolution in droplets of water and interaction with oxygenated water coming from the surface, and which this sulfuric acid forms and interacts with the bedrock, dissolving the bedrock, the carbonate bedrock, and depositing gypsum as a byproduct. And in a way, this process acts in such a way that, in essence, it mimics the morphology of the rock, so it can fully replace even structures. For example, if you have some fossils, let's say in this bedrock, the texture of the fossil can be largely preserved in the replacement gypsum, which can form in that place. Here you have a nice example of this kind of replacement gypsum crusts, for example. There have been a number of sulfuric acid caves registered in the world, and this is increasing. Like every year we have some new publication, new interesting findings. Ever since this topic was approached, or let's say it became a bit more popular, these kind of caves have been registered in increasingly more and more places around the world. Very nice examples. This is here in a cross section of a quite famous cave, the Frasassi cave in Italy, when you can see that actually the formation of the passages is tied to the former base level positions of the in the Frasassi gorge in the canyon, so the dissolution or the space, the cave volume formation is largely above the water table. And another thing that most of this oxidation of hydrogen sulfide happens in parts of the cave which are in which this limestone formation is uncovered, while in the parts where it's covered, the supply of surface oxygenated waters is minimum, and the oxidation is also minimum. So we can have also dissolution of limestone by dissolved H2S. So it's a weak acid that can also do some dissolution, but most of it happens in the area where it's uncovered and there is interaction with an oxygenated water coming from the surface. In this kind of systems, what is generally studied is the isotopic composition, can be the isotopic composition of the gas of the hydrogen sulfide which comes into the system. But most commonly it will be as some of these caves that have been studied are already fossil caves. So we have gypsum products, but we don't have any active degassing or water. So it will be the stable isotope composition of this sulfate gypsum, most commonly gypsum, but it can be also other sulfate minerals. So the sulfur isotope composition can help us identify the sources of sulfur, but also it can reflect the chemical processes around the sulfur pathway. And contrary to the situation, or let's say compared to the situation with the carbon isotope composition, it's much more complicated with the sulfur. It can be affected or modified by many more processes, and the fractionations are much more overlapping, so it's not as clear as it can be in other systems. On the other hand, if we also use the oxygen isotope composition, for example, in the gypsum or the sulfate minerals, we can identify the source of oxygen which was provided for the oxidation of the hydrogen sulfide. For example, the dominant sources are either water or molecular oxygen from air, which can be an indicator of the environmental conditions when this in this cave system. For example, whether it was more oxic, so there was a oxygen available in the air, or it was more an oxic condition, when then the oxygen for the oxidation of the hydrogen sulfide will be mostly provided by the water. In terms of sources of hydrogen sulfide in this system, it has been found that most commonly it will be microbial reduction of sulfate rocks. So sulfate rocks, so evaporitic rocks, will have a isotopic composition, which is largely positive, for example, 10, 50, plus 10, 15, 20, 25, and more, this kind of evaporative formation. And by their reduction in microbial reduction, where hydrocarbons can act as the electron donors, we can have formation of hydrogen sulfide. And this has been found as the most common situation, but it can be also a contribution for magmatic hydrogen sulfide, although this is much more rare situation, or not many examples have been found. You can find here on this graph a number of caves, sulfuric acid caves in the world with reported values of their stable isotope composition, or the sulfur isotope composition of their gypsum. What is interesting to be noted in this sense, you can see some large range in some of them, but quite narrow in some other, and that can be the result of either the complexity of the system, but also it can reflect the number of samples which have been done in a particular cave. So although we know a lot about this stuff, yeah, but there is still much to be done to fully understand the full extent of processes acting in this kind of system. As I said, the pathway, the sulfur cycle, or the fractionations in this with sulfur, associated with sulfur, are much more complicated, or it can be, the range of fractionation can be much larger. For example, but the possible range of fractionation by reduction of sulfate, it can be up to 60 per mil, for example. So the byproduct, the hydrogen sulfide formed by reduction of evaporitic rocks, can be about let's say up to about 60 per mil lower than the source evaporitic rock. For example, if that was plus 20, the product hydrogen sulfide can be then minus 40 per mil. And this will depend whether it was aerobic or anaerobic, or for example, in the opposite manner, the oxidation of the hydrogen sulfide, let's say, the fractionation will be different, whether it was in the whether it was microbial, whether it governed, whether it was abiotic, or whether it was in oxic conditions or anoxic conditions. So all of this can have an effect, and in the end, even though the situation, let's say in terms of sources, can be even supposed by other means, it's not so straightforward to determine the source by looking at the sulfur isotopes, because it could be largely modified and not by overlapping processes, or processes with overlapping fractionation values. This graph was already shown in Bogdan's presentation. It's a nice example from Chernobyl that he's already mentioned, and I don't want to go into detail on this. I just want to point out this aspect about different processes producing different outcome. For example, the source of the sulfur for all of this is evaporative formation, which has this plus 17 per mil composition. In the end, due to various conditions, let's say the type of reduction, whether it was the electron donor limited or it was the sulfate limited situation, it produced different kind of values, which in the end it reflected in the gypsum which was formed. For example, from the same source, we can have gypsum having a composition of -7 per mil, or -25 per mil, or plus 17 per mil. So to better understand this, it's important to study also the oxygen isotope composition in addition to the sulfur isotope composition, because in the end, if we just studied the sulfur, it wouldn't have been possible to identify these processes or the pathways that were involved in this kind of system. Here's another example of using both sulfur and oxygen isotopes from gypsum, in which it has been identified that the strong covariation of both sulfur and oxygen. Actually, this is a somehow high resolution study of these gypsum isotopes, or these gypsum deposits in a sulfuric acid cave. And it has been found that most of the oxygen comes from water, and more positive values are actually reflecting higher contribution of oxygen from the atmosphere, so for molecular oxygen. So it means more oxic environment. So in a way, this oxygen isotope composition reflects the environment under which this oxidation of hydrogen sulfide happened. And the fact that they're highly correlated indicates that this process was affecting both the sulfur and the oxygen isotope during this process of H2S, or the hydrogen sulfide oxidation. And to summarize all of this, I will, as you could see, few examples. The stable isotopes can be really useful to study, to identify hypogene, first to identify hypogene karst, whether certain minerals formed by these hypogene karst processes, or whether a bedrock has been affected. There have been some alteration of the bedrock stable isotope composition. And also they can help us to study the processes or the characteristics of those hypogene karst systems. The most commonly until now, what has been applied is the carbon, oxygen, and sulfur stable isotopes, but it's not the only thing which has been applied. This, as I emphasize, it's the most commonly. And most commonly, this has been done on the basis of cave minerals, but there are some examples, or let's say more examples also, where the groundwater has been studied or the gases have been studied, and there's much more potential to be applied in a more complex or holistic sense, this kind of study. In any case, even after all of this, there's still much to understand about how these systems function in terms of their stable isotope composition and the variations possible and the processes which are operating. And there are many possibilities still open for application of even novel, let's say, stable isotopes, or something which hasn't been applied to this kind of system. For example, some have been, like the strontium isotopes, but there's potential to apply calcium isotopes, magnesium isotopes, and recently the, let's say, carbonate clumped isotopes have been applied to identify the temperature or the paleo water composition of this kind of hypogene karst systems. So that will be all from me. And if you have any questions, please ask.
Thank you, Marjan, for your great presentation. Any questions? So I have a question as usual.
Please do
for
so.
example, let's take if you go to a hypergenic karst system, you find also mineral deposits, you find some thermal water, you find also some gas emanation. How important is to measure, for example, the carbon from each three phase and to see the fractionation? Can it differ from one system to another?
Sure. Thanks. Sure. In essence, it's not a common situation when you have the chance to study all of it. That will be kind of a perfect situation if you can just combine all of it, all of the possible phases of a certain element in these isotopes, and to determine the possible processes which are affecting each step of a transition from one phase to another. As I mentioned, most commonly what we deal with is we study fossil cave systems, or even surface remnants of some kind of a cave system, to try to interpret or identify the previous operating processes. But yeah, if there is a possibility to do so, it's always good to obtain the as more as possible in this kind of sense. So it can be quite complicated depending on with which kind of element you play with. Let's say, as I mentioned, with sulfur, it can be quite complicated, and especially in active systems, as has been shown, you can find situations where, for example, in the same, let's say, a small river, sulfidic river, let's say, you will have a place when there is an active oxidation, but in another sector there is an active reduction. So it can end up being a much more complicated than this systemic way in which is being presented. So yeah, it will be of help if we can obtain more from the same system. Yes.
Thanks, Marjan.
So since I noticed that there are some other people in the audience that use sulfur isotopes, I would just make a comment. I mean, the presentation was great. I just wanted to re-emphasize that for whoever is doing hypogene, sulfuric acid spirogenesis, hypogene kind of studies, it's essential not to, I would say, draw conclusions just based on the sulfur isotopes, because that particular value that you are seeing there, if you do only sulfur isotopes, it can be misled. It's exactly like Marjan showed, you know, very widely, and it's pretty large in some places, very small in other ones. And so since not always you know where exactly you started with to apply and see what the value was, it's pretty difficult. So I would always suggest to have the oxygen isotopes as possible, because that will give you an additional information on the environment, whether it was steam, gases, or it was meteoric water, or you can have thermal water, you know, and then the values, at least in Cherna Valley, thermal water, delta O18 and meteoric water would have been different. And the gypsum or other sulfides that precipitate out of it, the isotopic composition was different. So this is very important, because once in Carlsbad, Lechugia, they noticed the values were so negative, or, you know, then they would say, oh yeah, this is hypogenic. Not always a negative value would be hypogenic. So pay attention to this.
Thanks, Bogdan. A comment, because in both presentations, Cherna Valley popped up, like also in Bogdan's and also in Marjan's. Just to, in my opinion, Cherna Valley is quite unique. Together with Marjan and also your former student Aurer and the bigger team, we were in the Cherna Valley 2019 and did almost a full, really nice sampling campaign. We collected not just the thermal waters, but also the dissolved gases, noble gases, isotopes of ethane, propane, and so on. So we tried to figure out the holistic view, how the system is working. So Genome is a really nice example where you can do stable isotopes in different phases and in a really small space, let's say.
Yeah, and those studies that we have done. So I have two a master student, a PhD student working on that project, and basically we had all the oxygen and oxygen and sulfur isotopes in all the water and all the minerals. So we sampled from upper Cherna Valley to the lower Cherna Valley. We did it, and we did some carbon as well, but we did not do any gases, anything else. So we used some of the results of your former Professor Cosma, who did some work early time there on the valley. Yeah. But yeah, a broader picture will always help you in drawing solid conclusions.
Yeah. Any other questions? If not, then I would like to thank Bogdan and Marjan for the two nice presentations, and we could see a really nice overview how we can use stable isotope in karst system, both epigenetic and hypergenic case. So thank you, and see you next week.
Thanks for having us.
Bye, everyone.
Bye.
Thank you a lot. Bye.